Here we are going to revise the theories about tangents. Okay. So what is a tangent? Tangent is a straight line that has only one point in common with a circle. So that's what the definition says. So we'll look into a diagram and see what's that. So if you look at the figure 3, this circle and this line has no points in common at all. And if you consider this figure 2, this circle and this line has 2 points in common. Those are the intersecting points. And if you consider this figure 3, this circle and this line has only 1 point in common. So we can say this line is a tangent to this circle. Okay, that's what the definition of a tangent says. So that's not much. Okay, so we'll proceed with that. So we have some theorems regarding the tangents. So this is the first. The straight line drawn through a point on a circle and perpendicular to the radius through the point of contact is a tangent to the circle. I'll repeat. The straight line drawn through a point on a circle and perpendicular to the radius through the point of contact is a tangent to the circle. So this is a property of a tangent actually. So we'll look into a diagram and see what this really means. Okay, so as you can see, this line is drawn through A. A is a point belongs to the circle. So this line is drawn through a point of a circle and a point of contact. The line segment drawn from the radius to the point of contact is perpendicular to the line BC. So if these two conditions are satisfied, we can say the BC is a tangent to the circle. Okay, so these are simple two properties of a tangent. I hope you can get that. Okay, now we have another theorem, which is the converse of the above theorem, that says the tangent through a point on a circle is perpendicular to the radius drawn to the point of contact. Okay, a tangent through a point on a circle is perpendicular to the radius drawn to the point of contact. That means, again, if this is a tangent, the radius drawn to the point of contact should be perpendicular to that tangent. That's what this converse theorem says. Okay, that's also not very much. So we'll move on. We have an example here. We are asked to find x and y. We are asked to find x and y. So I'll show you the steps again. We can say OC is equal to OD. OC is equal to OD because both are radii of the same circle. And that makes this OCD is an isosceles triangle. So ODC is equal to OCD. That means this one is also x. So if you consider the sum of interior angles of this OCD triangle, x plus x is equal to 180, sum of the interior angles. So that makes 3x is equal to 180. That makes x is equal to 60. So that's how you find the value of x. Then what about y? So this AB is a tangent to this circle, so that we know the radius drawn to the point of contact is perpendicular to the tangent. So this here is also x. So we can write x plus y is equal to 90. So since x is equal to 60, y is equal to 30 degrees. So that's how you solve a simple problem regarding this. So if anyone has anything to ask, any problems, any doubts, you can ask now. Why is 90? Yeah. If we go to the theory again, this theorem says the tangent through a point on a circle is perpendicular to the radius drawn to the point of contact. That means this the radius drawn to the point of contact is perpendicular to the tangent. So that we used that theory in the example. Uh, this is a tangent. So this is the point of contact. So the radius drawn to the point of contact should be perpendicular to the tangent. So OC is perpendicular to AB. That's why x plus y is equal to 90 degrees. This is a right angle. So this is y and this is x. So x plus y is equal to 90 degrees. I hope now you can understand that. Anyone is having any problems? Anything else? Okay. So we'll move on. We have another theorem regarding the tangents. This is a quite lengthy theorem. I'll read that. If two tangents are drawn to a circle, oh, this meeting will end in about 10 minutes, so please join again. This theorem says if two tangents are drawn to a circle from an external point, then they have stated 3 points. One is the two tangents are equal in length. The two tangents that drawn from an external point, they are equal in length. And second one, the angle between the tangents is bisected by the straight line joining the external point to the center. We will look at a diagram and see what they actually means. First, we will read out the theorem. The angle between the tangents is bisected by the straight line joining the external point to the center. We'll see what that means. Third point says the tangents subtend equal angles at the center. The tangents. So this property is about two tangents drawn to a circle from a same external point. Okay, so we'll look at the diagram and see what that really means. So this is a tangent and this is a tangent. Both tangents are drawn from the same T external point. Okay, so we are talking about these two tangents and the properties are described on these two tangents. Okay, so first property said two tangents are equal in length. This AP and AB, these are the two tangents. Two tangents are equal in length. That means these two are equal. So this is the first part of our theorem. And the second part, uh, the angle between the tangents is bisected. Please, can you increase the volume? We'll go to the next part. The tangents subtend equal angles at the center. This is a tangent. This is the angle that tangent subtends at the center. So this is another tangent. This is the angle that tangent subtends at the circle. So the theory says these two angles are equal. Okay, so you can prove these theorems, but we as we are revising, I'll just state the theorems as it is. Tangent subtend equal angles at the center. So these two angles must be equal. So those are the things that the above theorem actually have said. Okay, so you have to remember these three facts. The tangents are equal in length. The angle between the tangents is subtended by the line joining the point and the center, and tangents subtend equal angles at the center point. Okay, I hope you got this theorem. If you have anything to ask regarding these things, you can ask now. Otherwise, we can proceed to an example. Okay, so this is an example uh, regarding that. I'll leave it to you guys to try out first. I'll give you about 3 minutes, and then we will discuss the problem. Meanwhile, if you have any problems, you guys can always ask. Yeah. So the two tangents drawn to the circle are PQ and QR. QO produced meets the circle at S. So QO line is produced and that meets the circle at S. So that the PQS is equal to QRS, and 2 times OPX angle is equal to PQR. Okay, so we'll start with the first part. Okay, you can see PQ equals QR because from the theorem, these two tangents are drawn from the same external point. So tangents are equal in length. So PQ equals QR. And PQX is equal to RQX. That's also from the theorem. PQX is equal to RQX. So because the angle between the tangents is subtended by the line segment drawn to the external point to the center point of the circle. Okay, next. QS is equal to QS. So QS is this line segment that is a common side to both triangles. So you can write this using because two sides and one angle are equal in here. Okay, I hope you can get that part. So we'll go to the part 2. So to consider to solve the part 2, I'll again consider these PXQ and RXQ triangles. I can write PQ equals QR, PQX equals RQX, and QX is a common side. So in these two triangles, two sides and one angle are equal. So you can write Px is equal to Rx. Px is equal to Rx because corresponding items are equal. Then what you can write is QXP angle is 90 degrees. This QXP is 90 degrees. Why is that? Because from the theorems regarding the chord, you can that we have learned that the line segment drawn to the center point of a chord from the center to the midpoint of a chord from the center point of the circle is perpendicular to that chord. So using that theorem, I can write QXP is equal to 90 degrees and OPQ is equal to 90 degrees. Why? That is from the theorems of tangent. Uh, the line segment or the radius drawn to the contact point of a tangent is perpendicular to the tangent. So OPQ is also equal to 90 degrees. And we can write QPX is equal to 90 minus OPX. What is that? QPX, this one, is equal to 90 minus OPX, this one. Why? Because this OPQ is 90. So this part is equal to 90 minus this small part. Uh, then we can state that QPX, I'll erase these things. QPX, this one, plus plus PQX, this one, PQX, plus QXP, this one is equal to 180. Sum of the interior angles of this PQX triangle. And we can also write PQX is equal to 180 minus, this line is a simplification of the above line. So PQX is equal to 180 minus this QXP is 90 degrees. So this one is substituted. Sorry. So QXP is 90 degrees. So this is, it has substituted here, and instead of this QPX, we have substituted this 90 minus OPX. Okay. Then we can simplify. You can get that PQX is equal to OPX. Okay. PQX is equal to OPX. This small one. Okay. Not finished yet. Then we can write PQR. What is that? PQR. This big part is equal to 2 times PQX. Since these two are equal, this big one should be equal to 2 times a smaller one. So you can substitute that since PQS equals to OPX, you can substitute that here and then you can get the answer. We were discussing this example, and I hope we finished discussing this. And if you have any problems regarding this example what I have done here, please ask. Otherwise we can proceed to another example or following theorems. I hope not. So let's move on. Okay, so we have another theorem here. This theorem says the angles which a tangent to a circle makes with a chord drawn from the point of contact are respectively equal to the angle in the alternate segment of the circle. So this one is we look into a diagram and see what this actually means. So I'll repeat the theorem once. The angles which a tangent to a circle makes with the chord drawn from the point of contact are respectively equal to the angles in the alternate segments of the circle. So this theorem is shortly known as the angles of the alternate segment. So we'll see what that means. Here, this is a tangent, as you can see. This is a chord to the circle drawn from the point of contact of the tangent, and what the theorem says is this angle the tangent and the chord makes, this angle is equal to the angle of this alternate segment. So as the theorem says, this angle and this angle are equal, and the other side is also true. So this angle and this angle also equal. That's what the theorem says. So this angle and this angle are equal, and this angle and this angle are equal. So this is just another theorem regarding the uh, tangents of a circle. So if you have anything about this theorem, you can ask, or we can do some examples using this. Okay, let's proceed. uh, Here we have an example. Again, I'll give you some I'll give you about 2 to 3 minutes to try out, and I'll discuss this later. So what we have to do here is to find P, Q, and R. So you can use any theorems that we have learned so far. So you guys can try. While if you have any problems while when doing this, please you can ask. Okay, so the question here, we have to find P, Q, R, and S. So I'll start. We can directly write Q is equal to 30. Why? This is a tangent and this is a chord, and this is the angle that made by the tangent and the chord, and this is the alternate segment, and Q is the angle of this alternate segment. So from the theorem that we just discussed, Q is equal to 30. Then use likewise P is also equal to 30. So this is also an angle of the alternate segment, or you can say this P and Q are the angles of the angles subtended by the same segment. So P and Q is equal, uh, so that P is equal to 30 again. And you can write this, I'll erase this. You can write this AXE is equal to 90 minus 35, right? AXE, this one is equal to 90 minus 35. Uh, so AXE should be equal to 90 minus 35, which is 55. And you can get R is equal to AXE. Why? This is the AXE and this is the angle of the alternate segment. R is the angle of the alternate segment created by this AEX chord. So AX, since AX is equal to 55, R is also equal to 55. Then you can write CXD, I'll erase this. CXD is equal to 90 minus 30. CXD, this one is equal to 90 minus 30. So 90 minus 30 is 60. And considering the sum of interior angles of this triangle, you can write CXD plus P plus S plus R is equal to 180. So we know P, we know R, we know CXD. So you can find out S. So S is equal to 35 degrees. So that's how you get the answer. So if you have anything, any problems regarding this discussion, you can ask now. P equals 30. How it came? Yeah, P equals 30. How it came? So you can see this angle and this angle is subtended from the same chord CX. So these two angles are equal. Since Q is equal to 30, P is equal to Q, so that P is equal to 30, right? So those are the theories regarding the circle that we discussed about few more weeks ago. I hope you are now clear. If anyone is having any problem, anything else, you can ask. Okay. Uh, so if you don't have any problem, we can move on, right? So those are the things I wanted to discuss regarding this tangent and the cyclic quadrilaterals. Uh, Now we can do some past paper questions, MCQs, as well as the essay questions. So we'll try some questions now. Yeah, I'll give you about 2 to 3 minutes to try. This is the question from the 2016 paper. You are asked to find the value of x. Okay, I got some answers. Yeah, they are correct. Mm, yeah. So as most of you guys are finished, I'll start discussing. Uh, You can see this ABC is an isosceles triangle. So this angle is also equal to x. Since this CDEF is a cyclic quadrilateral, this x is equal to interior opposite angle. So x is equal to 65. So you can get that answer simply. Okay. If anyone has any doubt regarding this, you can ask. Uh, Otherwise, we can proceed. Okay. We will go to the next question. So here we have two questions. Both are from the 2016 paper. I hope we did the 19th question at the previous session. So you can try the 18th one now. No need to do the 19th one. See? So you are asked to find the value of CDA. Okay, I got the answer from 4 people. So I think others also have done the answer. So I simply just discuss this. They are asking to the they are we are asked to find the value of the CDA. So you can see this ABCD is a cyclic quadrilateral because all the vertices are lie on the same circle. Uh, so this this angle plus this angle should be equal to 180 because these two opposite angles are supplementary. So 80 plus something is equal to 180. So CDA is equal to 180 minus 80, which is 100. Okay, I hope you got that. We'll go to the next question. This is an essay question from the 2016 paper. Uh, I'll leave it to you to try first, then we can discuss. Okay. If you are done, you can send me the value of ACD in terms of x, and then you can no need to show me how you do the proving of the AODC is likely quadrilateral. Like this. Okay. Mm, one person has. Yeah, so yeah, she is correct. I'll give you about a minute and then we can discuss. Uh, if you have anything to ask about this, feel free to ask. Yeah. Shall I discuss? Okay, I'll do. Mm, okay, I'll read the question first. The center of the circle in the figure is O. AB, BC, and CD are chords of the circle. P is the midpoint of AB. The line drawn from P through O meets BC at D. It is given that AOP is equal to X. Find ACD in terms of X and show that AODC is a cyclic quadrilateral. So first we have to find ACD in terms of X. Uh, I'll construct this line. If you consider this, okay, first you can see this angle is 90 degrees, right? Why? This AB is a chord, P is a midpoint of the P is the midpoint of the chord. So OP is the line segment drawn from the center to the midpoint of the chord. So from the theorem, the AB should be perpendicular to OP. So this BPO angle is 90 degrees. So if you consider this AOP triangle and BOP triangle, these two sides are equal. These two angles are equal. This is a common side. So this BOP angle also should be equal to X, right? There is no problem about that. So BOP is equal to X. So that we can write AOB is equal to AOB is X plus X 2X, right? Okay, so AB is a chord. AOB is the angle subtended on the at the center point, and ACD is the angle subtended on the center by the chord AB. So ACD should be equal to half of this AOB, so that we can write ACD is equal to half of AOB. Half of AOB means X. So we just found ACD in terms of X. If you have any problem, you can ask. Okay. I'll erase these things here. Right. So we found that this is equal to X. Okay. So we have to prove this AODC is a cyclic quadrilateral. AODC, this one. Okay. So this AOP is the external angle so formed by reducing this DO side, and this is the interior opposite angle of the AOP external angle. You can see this AOP and ACD are equal, right? Both are X. So this is a property of the cyclic quadrilateral, so that we can write this AODC is a cyclic quadrilateral. So we use the theorem that we just discussed. Uh, the exterior angles are formed by reducing a side is equal to the interior opposite angle. Okay, I didn't. Okay, I'll explain that again. Mm, I'll explain that again. So we just found that this ACD is equal to x. Okay, uh, and this angle is also equal to x. So if you consider this AODC quadrilateral, this x is the interior opposite angle of this x angle, right? This is an external angle. This is the interior opposite angle of this AOP. So here we can see the external angle and interior opposite angle are equal. That is a property of cyclic quadrilaterals. We learned that as a theorem. So we can write uh, if in a cyclic quadrilateral the external angle is equal to the interior opposite angle. So if interior exterior angle is equal to the interior opposite angle of a quadrilateral, that should be a cyclic quadrilateral. We used that theory here. I hope you can understand. Uh, Otherwise, you can ask. I can explain again. This meeting is about to end, so you guys can join again. Please join.